Great.
Putting in progress, I know.
Zihao, do you want to do the introduction?
Oh, of course. Hello, everyone. Today we are honored to invite Jian Weng from UC Los Angeles. And Jian is a fifth-year Ph.D. candidate from UCLA under the guidance of Tony Nowatzki. His research interests mainly lie in designing and analysis specialized accelerators and their associated compilation techniques. Today, we will introduce the topic of synthesizing programmable accelerators. Let's welcome Jian again. And go ahead, Jian.
Okay.
We're looking forward.
Let me see. Let me switch to the first page of the slide. And then let me share the screen. Can you guys see my screen now?
Yes.
Yep.
Yes.
We got it.
Let me start and then minimize you guys. Can you see it?
Yep.
Yep. We got it.
Okay. Dear everyone, welcome to my talk, Synthesizing Programmable Accelerators from a Compiler Perspective. In this talk, I will present a compiler for domain-specific accelerator design automation. And since we do not have so many people here, feel free to interrupt me when you are confused. And let's start. This is motivated by the waning benefit of transistor scaling. Specialized accelerators emerge and already achieve big success in both academics and industry. For example, the number of specialized blocks on Apple SoC is increasing in the past 10 years. Both cloud service providers and hardware vendors have developed their own specialized accelerators, not only for NN models, but also for DB query. And a similar thing happens in the academics. So how are these accelerators designed? Designing a domain-specific accelerator starts with a set of target applications, and the developer study the program behaviors of interest and use their knowledge to develop specialized hardware mechanisms and evaluate it and implement it and evaluate it. Since it's a programmable design, software-hardware interface should also be considered, and as well as their high-level abstraction and the compilation techniques. It is a human effort-intensive process. Is it possible to automate it? As we can see, the idiom is the key. By idiom, we mean the program behaviors of interest, because this sentence is too long. I will use this in short. Can we just leave the hardware mechanisms in a library and take advantage of the compiler's awareness of the idioms to make the design decisions for us? And in our prior work, we did make our very first step to automate the design process of the domain-specific accelerators, and we to achieve that, we build a compiler that helps us make the design decisions. This is a compiler not for a particular architecture, but for a family of architectures. This compiler recognizes the program idioms and aggressively rewrite them in the accelerator ISA. And because the target architecture is agnostic, the compiler should keep robust across any design point within this family. And according to our evaluation, our compiler can achieve 2.5x speed up over an out-of-order server CPU. And we take advantage of the design automation infrastructure to study the progressive specialization. Next, I will give an overview of the target architectures and then discuss the capability of specialization. To designate the design space, we studied many prior programmable accelerators, and these three are especially representative. You notice that all these architectures tend to follow the same decoupled spatial paradigm. By decoupled, we mean the computation and memory are access are decoupled and specialized respectively. By spatial, we mean the timing, storage, computation, and routing is exposed to the ISA. Moreover, these architectures can be composed by connecting a set of very simple hardware primitives, as shown in the lower right of this page of slides. These architectures are attractive to us because of their efficiency, modularity, and flexibility. The basic principles of composing a design point is to represent the hardware in a graph of these simple components. We call this graph architecture description graph. This graph not only serves as a descriptor to the design point, but also as an abstraction to the compiler. To explain the decoupled spatial execution model, let's go through a very simple example. For this piece of code, the memory access and the computations are decoupled and they're represented in a dependence graph and mapped onto a spatial architecture. A spatial architecture typically refers to those architectures that consists of processing elements for computation and connected by on-chip network composed by switches for routing the instruction dependencies. And the synchronization FIFOs are injected. They not only serve as a interface of the operands, but also serves coordinates the timing of data issue and the instruction execution. This mapping is encoded in a bit stream, and the controller issues commands to the spatial architecture to load the bit stream to configure the spatial architecture. The memory access are encoded in control intrinsics and issued from the controller to the address generator so that the data can flow through the graph to execute the program. Under this paradigm, as long as the data access can be sustained, the graph execution instance can be fully pipelined to maximize the instruction level parallelism, which is the main source of the performance gain. Specific to our implementation, the host controller is a lightweighted single-issue RISC-V code. So programming a decoupled spatial architecture is essentially to encode and embed these specialized program idioms in RISC-V assembly code. Comparing against the conventional CGRA, the decoupled memory access keeps the computational resource, the processing elements, simple. Also, because of the memory accesses are encoded in idiomatic patterns, the memory requests are no longer fragmented scalars, which leads to better bandwidth utilization. But on the other hand, it explicitly separates the execution between the computation and the memory access, which brings the complexity to the compilation. So now we are done with
Jian?
Yeah.
What is on? So just to clear, the code on the right is the code you're proposed or the building, and the one on the left is the assembly code that is generating.
I mean, on the left hand side, it's the general proposed code. I mean, it's just you run the RISC-V code on a RISC-V CPU.
Right.
On the right hand side, it's the code. I mean, it's some pseudocode that will be encoded in the assembly code. I mean, in the RISC-V code, just in the instruction sequence that took the decoupled spatial architecture.
And the load config command there, what's the purpose of that, or what's
load config is to load the bit stream, load the dependence graph onto the spatial architecture.
Okay.
And the AN is the forward AN to, I mean, to the port A, something like that.
Okay. Yep.
And the data flows through, and finally we have, oh no, I forgot one instruction, which is the D. We were something here, the D will return back to the memory. Oh, I forgot that, I will fix that, and I will share the slides later.
Okay.
So we're done with explaining the decoupled spatial paradigm. So what's next? Considering the limited time, I will only cover how the computation and the memory access are specialized. Though we do have predicate-based conditional execution, this involves too many low-level technical details and microarchitecture stuff. So interesting, I will also omit microarchitecture, and I do have backup slides for that if you specifically have any question on that. I will open those slides. And I mean, though I do not cover the microarchitecture, one thing I do want to convey is that the more general specialized, the more expensive the architecture it is in power and area. And in this figure, we basically list all the dimensions we can tune for the target architecture. Does that make sense? And here we come to the computation. As I mentioned before, the graph execution makes the interdependent instructions fully pipelined. And what if we're greedy? We want something similar as the vectorization. We just duplicate the instructions and increase the bandwidth of the coordination FIFO. You may say, oh, there's nothing special for the vectorization here. But I want to present that the programmable data path of the spatial architecture offers better flexibility. For example, for FFT, though it's element-wise, it interleavingly does the addition and the subtract. And for complex multiplication, in an array of structured data layout, the data path is just irregular. And a reduction tree can easily be supported mapped onto the spatial data path. But I mean, it's only available on very advanced server CPU. So all these data paths can hardly be specialized on vector machine, but can easily be mapped onto the spatial data path. So we're done with the computation specialization. And here we come to the memory access. So as I mentioned before, the memory access are included in control intrinsics. And we do not specialize the memory access in either scalar or vector. We view it in a more parallelogram way, streams, a set of memory access under the loop nest. And the memory address generator can do either dense or sparse. For our dense memory address generator, it supports up to 3 dimensions of canonical loops, and our sparse memory generator supports a hybrid memory access pattern. The inner dimension is linear and the outer dimension is sparse. All these shadowed parameters are the arguments to the memory generator control commands. Besides the capability of the address generator, another interesting part to talk about is the memory state. The first and the last iteration of each loop level is considered to be special. So we attach this information to the memory response, requested by the address generator. This information is useful, can be both used by the port, the coordination FIFO, as well as the processing element. In this case, say the port is vectorized by 2, and n is not divisible. Our port can take advantage of this information to implicitly add the non-divisible data residue. Another use case is the accumulator idiom for the processing element. Assuming each processing element has local register and supports conditional execution, then the data dependence, the data flow graph looks like this. And basically the control signal should tell the processing element 2 things: write the intermediate result to the register and produce the finalized result at the end of the first dimension. And all this information can be by nature encoded in this state of the stream. So we're done with the brief.
Can you go back to the previous slide?
Yeah.
Okay, so you mean the entire accumulation, this program can be encoded in the memory stream you mentioned?
Oh, sorry. So it's still decoupled spatial. So for the addition, it's offloaded onto the spatial architecture. It's offloaded to a processing element. And the register is inside a processing element.
Okay, so
maybe I can show you something about the microarchitecture, though it's not a good idea. It's a little bit complicated. So the function unit is for the addition. And the register file is for the, for the intermediate result of accumulation. And we have a control table whose key is the stream state. And the value is how it control the processing element. Okay, if the function unit should execute, should the result return to the register file, something like that.
So your design is basically you decouple the computation part and the memory access part. This memory stream you mentioned was and the state you mentioned was to describe the memory access part.
Yeah. So for the A, it's a memory stream. For the A, it's a memory stream. And for A dot state, it's the it's the state of stream A. If it's the last of the, if it's the, the last response of the stream, something like that. So we have in total 6 bits for that. As you can see on the left.
I see. Yeah.
Yeah. We use this information to look up the controller to control the processing element. Say we want to finalize the result. We want to reset the register, everything. Does that make sense to you?
Sounds good.
Okay. Let's go next. We come to the compiler piece. So our compiler is for domain-specific accelerator design automation. But when designating the design space, we should not assume our design space is domain-specific. Otherwise, we run into a paradox. We automatically design the domain-specific accelerator in a domain-specific way, in a domain-specific space. So, because our scope as a whole is domain agnostic, we cannot adopt a domain-specific language as our high-level abstraction. So here we adopt C. And this also allows us, leaves our programming interface open to be a backend for a domain-specific stack like TVM or Graphite, everything, something like that. And as I mentioned before, there are 2 key challenges of the compiler. First is that our decoupled spatial execution model makes explicit separation between the computation and memory access. We should determine how they are decoupled. The other is the architectures. So we are not targeting to a single architecture. We're targeting to a family of architectures with different features integrated. And to solve the first problem, how the program should be decoupled, we rely on the programmer to provide some additional information to the compiler, and we extend the 3 pragmas for that. And later I will talk about how we robustly handle the hardware in the design space. So as you can see, we have extended 3 pragmas from inner to outer. The offload pragma indicates the loop body will be, the computational instructions in the loop body will be offloaded onto the spatial architecture. The stream pragma indicates all the memory access below this loop body are restricted so that they can be safely encoded in the control intrinsics without hurting the original semantics. And the configure pragma annotates a compound body, which indicates all the offloaded region within this compound body are concurrent on the spatial architecture. And next, I will demonstrate how the compiler take advantage of this pragmas to analyze the program and rewrite it in the decoupled spatial way. Some LLVM pseudo IR will be presented, but I guess I promise it's okay, not I guess. I promise it's okay. You can get it without knowing what it exactly is. So on the left hand, it's the original program. On the right hand, it's the LLVM. The upper bar of Zoom, hides something.
Excuse me?
Yeah,
I mean,
we can't see it. Only you can see it. So
okay, only I can see it. Okay.
yeah, so it's not blocking anything for us.
Okay, it's not blocking anything. So all this. Where's my cursor? I cannot find my cursor. Okay, I can find my cursor now. So all these pragmas are encoded in metadata and hint intrinsics in the AR. And then our compiler starts with the memory operations in a block that's annotated with offload. And all these memory operations and as well as the pointer computation are annotated, are marked as the memory operation, will later be fed to memory access analyzer. And all the operators that consumes the memory operations are considered to be computational, which will be represented in a dependence graph and fed to a spatial to the spatial architecture member. So for this dependence graph, these computational instructions are fed to a spatial member, and we get a spatial mapping. And these memory operations are fed to a memory analyzer and include them in control intrinsics. And for now, we have the memory access included and the spatial mapping. And the last step of the compilation is to embed them into the decoupled spatial, into the RISC-V assembly code. What should we do? What we do is that for the load configuration instruction, it is injected right after the configure.begin. And for all the memory operations, they are hoisted outside the loop, no higher than the stream level. And for all the instructions that's executed by the specialized units, say either the spatial architecture or the memory access generator, they are removed. They're just removed. Then we have an empty loop. And finally, we invoke a O3 pass to clean it up. It is the dead code elimination. And finally, we get this piece of code, and we execute this piece of code to execute decoupled spatial architecture. And to put this piece of program on the decoupled spatial architecture.
So the whole compilation flow is based on LLVM.
Yeah, the whole flow is based on LLVM.
And the memory access transformation, did you write it as a pass or?
Okay,
from
I will later discuss that. That's a very good question.
Another question is all computational patterns can fit into the 2D grid template on the right?
I mean, you mean what happens if the computation does not fit in?
Yeah.
I will also talk about that later.
Okay, thank you.
Oh, Jesus, I must spoil. I just want to pretend I finished it. Okay, we just skip this page, pretend you did not see anything. Here we come to the idiomatic transformation. So we analyze the software idioms and inspect the hardware capability and rewrite it accordingly sometimes maybe the hardware specialization is not available. We need to, we need to implement a backup transformation that escapes using that feature. For example, if sparse memory address generator is not available, what should we do? I will later discuss it. Then let's go through idioms one by one. Okay. First, come to the idiom that we are already very familiar with, which is the accumulation. So if we just use the vanilla graph on the down right, on the down left, then it's just inefficient because it's bounded by the latency from C to B to C. And in this case, in the compiler, we can detect one of the operand is just the adder itself. It's the addition itself. So the accumulation is detected. And we have P local register and the conditional execution and the true state. We will transform it into this graph. It's just a recap. Next, we come to the resource allocation. So our compiler has the capability to determine, how many instructions are offloaded onto the spatial architecture and how much resource should be allocated for each concurrent region. So in this case, so this 3 code regions has different execution frequency. And for the one with the higher execution frequency is favored to occupy more resources. And for the scalar region, they're even more favored offloaded to, to some shared PE. They can share the same processing element. So, the point I want to make here is that our compiler may prioritize it, but if something does not fit, our compiler may drop it according to the execution frequency and fall back to the host call execution. Does that make sense? Does that make sense to you?
Yeah, it makes sense. In your program, I saw that there is some data dependent loops. J is dependent on the range of J depends on K.
Oh yeah. So there is some data dependence. So that's something I omitted in this talk too. So there are 2 kinds of dependencies. One is the forward, the other is the backward. We first talk about the forward dependence since it's the same. Okay.
Okay.
The inf is used by this one. And the inf sqrt is used by this one, right?
Yeah.
So for this 2, forward dependence, as long as all these instructions are concurrent on the spatial architecture, they can go transfer bus from the output to the input without any intervention of the host call to asynchronously communicate. For the backward, dependence, it's a little bit complicated to analyze that. For now, our solution is just put a barrier right after each iteration of K, wait for the pipeline drain. Though it does help if we can, send the very first iteration result to the green region, It may help to hide the latency of the division and the square root, since these 2 operations are expensive. So it does help. Maybe
I see.
Yeah. 10% enhancement. If in menu programming, this can be, this is just dangerous to do that. In menu programming, we can do that. And so we're done with clarifying compiler has that capability. And here we come to the vectorization. So for the vectorization, as I mentioned before, it's just to enumerate the unrolling degree and duplicate the instructions. but we should follow some idioms. If the instructions are just element-wise, then we just increase the bandwidth of the port and duplicate the instructions. If some data is a looping variant, it should not be, I mean, we have no bandwidth to increase. It should just be broadcasted through the network. If it's accumulation, we need to, I mean, do a reduction tree style. And all these transformed graphs will be fed to the spatial mapper. And then the spatial mapper will give a feedback to the compiler. If it's a success, if it's successful, how good is the performance? If it fails, the compiler will try a more conservative resource allocation. Does that make sense to you? I need some feedback since just now you asked the question of the resource allocation. Okay.
It sounds like a try and error.
Yeah, try and error. Yes. And then here we come to the memory access. So we first we start with the simple thing, the dense memory access. So dense memory access can be 1D, 2D, or 3D. And thanks to the, to the TVM analysis infrastructure, there's a linear detection interface, and which hints me all these dense memory accesses are essentially a linear combination of the looping vective variables and the looping variants plus a base. And I develop a data structure to record the result of memory access and extract all these shadowed parameters, shadowed values, as to generate the control commands for the dense memory access.
What do you mean by trip minus count here?
Trip count, not minus. It's
sorry.
Trip count. Since the trip count can be, trip count can be also a vector, since it's a loop nest.
Okay.
And for the dense memory access, once it's analyzed, we find the two idioms are especially useful and useful for to optimize. One is coalescing, the other is fusion. Coalescing is that you manually unroll the loop, and you have AI plus 0 and AI plus 1. And these two memory accesses are just interleaved. And if they are instantiated in two different streams, the streams send the memory request in the granularity of the cache line. So the same cache line are requested twice, and half of the memory bandwidth are wasted. And in this case, we can notice these two memory accesses are exactly the same. Only the difference is the base. So they can be coalesced into one by appending a new dimension after. But after that, it makes the things even worse, since because of the implementation of our address generator, the state machine. The state machine can only handle up to one dimension, and this dimension is short. So a cache line is requested by size divide 2 times, which is even worse. But fortunately, it's a false positive. These two dimensions are actually continuous. So we just fuse these two dimensions into one. And finally, we can use the network to distribute the data to their operands. And meanwhile, we fully utilize the memory bandwidth. And
that's presumably is dependent on the underlying memory hierarchy, though, right? Like knowing the size of the cache lines and whatnot.
No matter the cache line it is, it cannot be two elements, right? A cache line cannot be as small as two elements.
Mm-hmm.
And this transformation does not hurt the performance. It at least in your case, if there are just the two elements in the cache line, then we just, does not improve the performance. It doesn't.
Yeah. Yeah, that's a good point. Yeah.
It's a generic and feature independent. Transformation.
I see. Yeah, makes sense. Thank you.
And here we come to the idiomatic specialization in sparse memory. Sparse memory is a little bit complicated. To analyze the expression tree looks like this. We extend the three kinds of nodes: addition, invariant, and load. Addition is something similar to linear combination, but in linear combination, each term is involved a loop variable at the very first order. And addition is just add two values that can be recursively stripped. And for invariant is a special case of linear combination, assuming all the coefficients are 0. But we do need this node, since if we don't have this node, we run into an infinite recursive analysis. And the load is just a load from the endless memory. Does that make sense? I think that makes sense. Okay, here we come to the most general, but we put it all together and analyze this most general index expression. So we start with a linear combination. Since they added by j, the j is the loop variable, so it's a linear combination. And the base is a binary addition. The left-hand side is the key, which is the loop invariant. The right-hand side is the load to a dense memory. And finally, we get back to the analysis of the degree, which is a load of the linear combination, a load of dense memory.
Regarding the invariant, is it used in dense memory access as well?
Yes. So, finally, we make them, on this one, we do not have a concept of invariant.
Yeah.
In this one, we finally additionally introduce this invariant concept. And I just say, I develop a set of 3 nodes that as a wrapper that represent the result of the index analysis. And each attribute can recursively be an attribute, and the leaf is the invariant. So we're done with analysis. And here we come to the code generation. And we look at the binary addition, and the key is the offset, the starting address. And if sparse address generator is supported, we just generate the code that utilize that unit. But if it's not available, we need to fall back to dense memory access generator. So the outer loop is still kept, and inside this loop, it repeatedly generates a dense stream to the destination port.
Is indirect memory intrinsic in your?
Yeah, it's control intrinsic. It's a control intrinsic. It's the offset is from this stream, and the trip count is from the other stream.
Yeah.
Starting address is key, and finally the data is forward to data port. Yes.
Just a stupid question.
No question stupid.
Okay, so do you support multi-level indirect memory?
Yes. Yes, we can support multi-level indirect memory, but the problem is that maybe you can do it to say 100 level. That's impossible because you run out of the bookkeeping slots on the stream table.
Okay.
Yeah.
Oh, yeah.
But you can do a pointer tracing as long as you can. As long as you can tolerate the latency from the input to the output.
So you mean there are not the number of slots in your memory state number limited by hardware, or?
Yeah, limited by hardware. we have some bookkeeping slots in the hardware, in the address generator.
Is it customized value?
Yeah, it's a customized value.
So,
Wow, you notice there's a very low level technical detail. Maybe you just
okay.
will not give a number of 6 or 8. That's already enough. Maybe 4 is already enough.
So the design choice is based on the common workloads you're dealing with. Is that right?
Yes. Yes.
Okay. Sounds good.
So finally, just to give an overview of the design space exploration. As I mentioned before, our compiler has the capability to transform the program into multiple versions of the intermediate representative, like different unrolling degree, different target, available features like that. And then this transformed intermediate representation are mapped onto the candidate hardware. And these software hardware pairs are fed to the design space explorer. This design space explorer does a evaluation, estimates the software hardware affinity, and they use this information to guide the hardware evolution and modify the hardware. Once the hardware is modified, we remap it and repeat this process and until the candidate hardware converge.
Oh, this looks cool, but how do you evaluate the pair?
Oh, wow. Then this is the backup slide. So we evaluated in 2 pieces. One is the performance, the other is the power area. So for the performance, as I mentioned before, the main performance gain of a decoupled spatial architecture is the instruction level parallelism on the spatial architecture. We just count the number of the spatial instructions on the spatial architecture and the time set by the activity ratio. The activity ratio can be affected by the the activity ratio is determined by the data availability. Data availability can be bounded by the memory bandwidth, bounded by the output, some value routed from the output port to input port, bounded by the latency, something like that. We count this number and then estimate the activity ratio and get the instruction level parallelism. And for the power and the area, we do not synthesize the hardware since it's time consuming. So what we do is we synthesize each component standalone with different parameters. And we use a regression model to predict the hardware cost and add them up. And there's only maybe 5% of difference for the timing buffer comparing with the real hardware. And we use this too, and use the performance per area as our objective function to evolve the candidate hardware. Does that make sense?
So this is a cost model stuff.
Yeah, it's a cost model. It's an objective function. And here, shall we go to the evaluation?
Yeah, go ahead.
Okay, let's go to the evaluation. So we first evaluate the performance of the compiler on 3 sets of workloads: max suite, a benchmark suite for accelerator design, DSP, a set of inductive matrix algorithms, which was from my first paper, and the VITIS, which is the Xilinx HRS workloads. And the baseline is the vanilla C code compiled with GCC 03 enabled on AMD and run on AMD EPYC 7702P, a very powerful server CPU. And we implement our architecture by extending chip height and synthesize the synthesize the generated RTA on Synopsys design compiler at 28 nanometer technology node. And we model our performance on Gem5 extended RISC-V assay, extend our control instructions, and integrate a cycle-accurate spatial simulator. According to our evaluation, the difference between the RTL simulation and the functional simulation is within 5%. So it's already very accurate. And the base transformation is just we decouple the instructions and encode the memory without any optimization. This is the performance. And incrementally, we implement the generic optimization, which is the memory coalescing and dimension fusion. So workloads benefit like stencil, FFT, and grayscale, since we inevitably need to unroll the data, unroll the loop, and gather the data within a small window. WinW is the same case. Temporal is the case that we enable the hardware capability to, multiple instructions and sharing the same PE. And next is dynamic. Dynamic means we give the capability to the on-chip network back pressure. And the merge sort is the only one, benefit. It's essentially a key value join. The data consumption rate is highly data dependent.
Sorry, let me, what is this showing? What are the units on the y-axis?
Well, the speed up. Sorry, it's the speed up.
I see. Okay.
Over the this CPU over the out of order server CPU. I mentioned.
I see. And so are we starting? Oh, so base is where we're starting from.
Base is where we're starting from. It already, does decoupled spatial transformation.
Okay. So we're comparing to CPU implementation. Base is without any specific features turned on. Like, am I supposed to interpret generic, temporal, dynamic, and indirect?
True.
Okay.
True.
Okay, thank you.
Indirect is the sparse matrix. Generation.
So what is the criteria you select the baseline CPU? It should be, you can use the greatest one or use the most poor one.
What?
How do you select the baseline CPU, the out of order CPU?
How do I select the out of order CPU?
Yeah.
Just choose our most powerful CPU.
Okay, so to be a fair comparison, it should be, say, the same power or the same transistors. I'm not sure what criteria you're.
Or maybe true. It's not normalized. If we are doing an area normalized performance, that should be 100 times higher.
Oh, I see.
Yeah.
And this performance you demoed is not normalized.
Yeah, it's not normalized. It's just our compiler on that. If we do an area normalized performance, even for single core, we just cut a single core of the EPIC CPU from the diphoto, we still have 100 times the speed up, 100 times area normalized speed up.
I see.
Because we are specialized for the interdependent instruction pipeline. No matter how wide the issue window of a out of order core is, it cannot achieve that effect.
Yeah, another question. There is a merge sort in your benchmark. Is that right?
Yeah.
I think people need to write a recursion to implement that merge sort, and to support recursion, you need to have something like stack.
No. So
Oh,
Recursion essentially, in terms of Turing completeness, you can always rewrite a recursion into a non-recursion version, right?
that makes sense.
Yeah. And in merge sort, we can do something pretend we are recursive. Something like I sort length one array in the first pass, separated them, I partition them in chunks and sort length one array in the first pass.
Yeah, that makes sense.
Double it.
You can
And
keep doubling it until.
yeah, and after that I do a synchronize after each pass. So it's equivalent to recursion, but it's not a recursion.
But do you need to say revise a program in the benchmark? Or?
Yes, we do. I mean, we do make some rewriting. Either, no, not either. Mostly to make our compilers' life easier to detect the idioms.
Yeah, I think there should be a rewrite test.
Some rewriting is required, true.
Okay, thank you.
Can we go to next slide?
Go ahead.
Okay. So next we study the behavior of different specialization. We do have area normalized performance and the normalized again. So in total, we build 3x3 9 accelerators. The first 3 is the 3 sets of the workloads. The second 3 is the degree of specialization. So at the very beginning, we just specialize the hardware capability. By capability, we mean, say, oh, this sets of workloads are all dense memory access. Then we do not give it the sparse memory access generator, something like that. Second, we specialize the functional unit. Like if a floating point is not used, we just trim it off. Finally, we do the topology. So the data path of the spatial architecture is specialized for the dependence graph within that subset of the workloads. And we use the performance per area as our objective function. And all the numbers are showing percentage, means that they are normalized by the best objective function. And here we come to this graph. We build an accelerator for VTS, and it achieves the best performance per area because first we normalize first we just have the dense memory access. But then dense memory access, then we trim off the floating point unit. And finally, since in VTS, most of the memory access, most of the data dependence, the data dependence graph are element-wise. So the excessive routing resources are trimmed. And the similar thing for the DSP. But it's tricky for the max-to-eat. Max-to-eat does the best for 6 workloads, and 5 of them requires the indirect memory access, requires a sparse memory access, which is MD, MD, NW, Radix, CIS, and LPAC. And the merge sort is the one with the dynamic memory access. No. Then the back pressure, on-chip back pressure. And the Vita-B, Stencil 2D, 3D, and these 3 are element-wise and the dense memory access. So those hardware resources are wasted. So they are actually better specialized by DSP and VTS. But in general, look at the geometry. Max-to-it is the specialized accelerator is still best specialized for this subset of the workloads. And this too has no surprise, since it's not the worst. Since the other two architecture are both, for Vitis, it's simple. So the other two architectures are overkill for that. So which lowers the objective function. And for Vitis, since the integer capability is trimmed, so it's not capable for DSP and and Vita-B in Max 8. So they fall back to CPU and achieve only 1 or 2% of the objective function. So does that make sense? Do you have any comments on that?
What is FU?
Functional unit.
Oh, I see.
Like some data type I don't need, I just trim it off. For Vitis, they are all, how to say? For Vitis, they are just all integer.
Yeah.
So for those floating point, they fall back to CPU with low performance.
I see.
And finally, we conclude my talk. We build a compiler that unifies the compilation for decoupled spatial architectures. And this work suggests that compiler is not only for the productivity of writing code, but also help us better understand the hardware software co-design. Program idioms are useful for both specialized compilation and making design decisions. And the granularity of defining a idiom should not hurt the modularity. By modularity, which is how big the scope of a idiom should be. And how many times do we have? Maybe 5 to 7 minutes. Then let me talk about the future work. So we have two directions of the future work. One is purely on PPT and the other is ongoing. The first one, FPGA prototyping, is ongoing. And along with the FPGA prototyping, we also want to do multi-core scale-up. And this course can be asymmetric, can be heterogeneous. Maybe some core are bigger and more powerful, and some core are smaller and less powerful. As well as exploring the design space of memory hierarchy. And here is a preliminary result. So we have a comparable execution time or even faster than high-level synthesis, but with a significant faster compilation. Since the high-level synthesis can only, in some ways, our accelerator, design space exploration is say high-level synthesis for a set of applications instead of a single one. For high-level synthesis, it requires to resynthesize the whole design for each application each time, so it's time-consuming. But we map it to a chorus grain reconfigurable accelerator, where the compilation can finish in seconds. So these are preliminary results, and we will have more benchmark available later. And the next is I have an idea on the virtualization of the specialized accelerators. Unlike run on ASICs, each application runs on its dedicated hardware, so there's no resource contention. But the things becomes different when we run the applications on programmable accelerator. In academics, it has long been claimed that the programmable accelerators can be used to unify the ASIC ocean. But is that true? How can we deal with the concurrency and allocate the resources when mapping multiple applications to the programmable accelerators? So we should do the same thing as we have already done on the CPU. Say we should create an illusion to the applications that they are occupying the whole hardware resources. And somehow we need to develop mechanisms for hardware for the applications, the task scheduling and the task isolation. For task scheduling, since in this case, the number of resources required are transparent to the operating system. And we somehow need to determine how to assign a task to a hardware. And for the isolation, so there are two ways of isolation. One is that we do static or spatial isolation. We just map them to different processing elements for two different applications. This requires us to polish the algorithm of spatial mapping. For now, the spatial mapping in some very tough case, maybe still takes minutes. And another is we dynamically do that. We share the PEs, but we use the tags to isolate the workload, workloads. And so this is a very preliminary idea, and I'm open to discussion with anyone if you are interested. And thank you for listening. If you have any further questions for me, you're welcome to ask.
I think some people have already go for lunch.
Yeah.
The idea of the visualization stuff looks very promising.
But I need this, and but looks like it requires intensive engineering efforts, excessive engineering efforts.
Yeah, we can discuss that offline.
Yeah. Yeah, it's ongoing. I just have the idea, but for the FPGA prototyping, we're still working on that. And it's becoming real, more and more real.
Hi, thanks. This is a great talk, and I have a question about your this project. In like TVM or Halide, they have their own like scheduler for like transforming their computation and create an auto schedule to optimize the computation. So is your like compiler or this methodology compatible with their workflow, or you think it's orthogonal and their optimizations can be implemented in terms of your compilation flow?
So I think, as I mentioned in which slide, let me find that slide. I think it's this slide. As mentioned, so an important design decision we make is that we adopt a general purpose programming language instead of a domain-specific one. And I emphasized that our programming interface leaves open to be a backend of TVM or Halide specialization. TVM or Halide, I mean, backend code generation. So the point I want to make here is that our optimization are conducted in a lower level. Unlike TVM and Halide, they mainly focus on the loop organization and mainly on the loop optimization. Even vectorization is a for loop. Even vectorization is a for loop. I mean, it's also derived from loop organization. But in my, compilation transformation, you can see it has a few things related to the loop organization, but we are open to be a backend of this DSL.
I see. Cool, thank you.
I believe the thing looks like TVM means LLVM, and your input is already LLVM.
So we start with a C code annotated with this, and I hacked the client front end so that it can recognize this bunch of programs and include them, could generate them in the metadata.
I see.
And And then I write a standalone LVM path just to follow the instruction in the hello world. I mean, write a path to transform the code. Do you have other questions for me?
All right, if I think that's it, I guess I'll stop the recording now. Is that good?
Okay, stop recording.
All right.